Hey everyone, welcome back. In this lecture, we're gonna go over chapter 4, moving average and smoothing. So starting from this chapter, we'll be learning a series of models that can be used to do economic forecasting. Let's get started. First of all, I would like to give you a general idea about the forecasting strategies that we usually use in practice. There are a couple of steps. In the first step, we usually pick the model. And the model that we will select depends on the nature of the data. Usually, we would analyze the data briefly to get a general idea about trend, seasonality, cyclical component, etc. Sometimes we even rely on our intuition about the data to pick the model. In the next step, we will split the data into two sections, one for fitting the model, and the other is for testing the model to see whether the model does a good job or not. In step 3, we will use the first part of the data to develop the forecasting model. Basically, that means we use the data to estimate the parameters to specify the model. And then we will use the model that is specified in the previous step to forecast for the second part of the data. Once we have the forecast, we can compare our forecast with the actual data and to see if our forecast is far away from the actual data or is close to our data. And that is to devaluate what we call forecasting error, okay? We, of course, would like to have forecasting error minimized as much as possible. Then in the last step is for us to determine whether the technique is sufficient or not. If the technique or the model we selected is sufficient, that's a good job, then we're gonna use the model to do the forecast. If not, we will need to further modify the technique, and usually we start from the very beginning, select a new model. We don't need to split the data anymore. We'll fit the model again and check the forecasting error to see if we can get a better model or not. Right? So next, I would like to talk about the forecast error. What is forecasting error? It is basically the cumulative difference between the actual value of our data and the forecasted error value using the model. Okay, so let me give you an example. Suppose I'm using the data and selected the model to do the forecast. And for one particular observation or one particular period, I find out using my model, the predicted value is, I'm gonna just kind of making things up. So we usually use Y hat to denote the forecast value. So I'm gonna say the forecast value is 12,000. Okay, it could be, say, quarter revenue for a company. And when I go back to my actual data, I find that for that particular period, the actual revenue is instead $13,200. I'm gonna need to put the dollar sign, okay? So apparently my forecasted value is different from the actual value, which you'll find quite common in forecasting. We can't build a model that can predict perfectly. There's always some difference between the actual value and the predicted value, which is fine. So now, if we take the difference between these two numbers, we will do Y minus Y hat to get the difference between the actual value and the forecast value, which is equal to 1,200. Then that is the forecast error for that particular observation. Okay, and if I do this for all the observations in my data, somehow put them together, that's why we say it's cumulative. Somehow if I put them together, that way I will measure the focusing error using my model for the data. Okay, now of course, as you can imagine, we want our forecast to be as close to the actual value as possible. And therefore, in terms of the forecasting error, we want it to be small, right? The smaller the forecasting error, the better the model can focus. And there are several ways to measure the forecast error. We don't just simply find the forecast error for every observation and add them up. And the reason being, for this example I give you, as you can see, the difference is 1200 positive. There could be situations where the predicted value is even higher than the actual value. Then when you take the same difference, you will find out the difference to be negative. And therefore, if you add up negative and positive numbers together, they cancel each other out. You're not really measuring the forecast error for the model. And therefore, we have the following alternatives, or actually the following actual measurement used in practice. The first one is the mean absolute deviation. If we take the absolute value, then we can get rid of this negative positive canceling each other issue. We got positive numbers all the time. We add them up, divide by the sample size. Then we get one measurement to measure the forecast error. An alternative, another way to do that is the mean squared error. Instead of taking the absolute value, we can square the difference. And that way, we also turn negative values into positive. Still, we divide by the sample size to get the average squared error. That's another measurement. And the third one is called the mean absolute percentage error. This can be used to evaluate different techniques or two different scenarios. For the first two, they kind of depends on what techniques you use and depends on the data. But for the last one, you can compare between different models. You can also compare between different data sets. So these are the three measures that will be reported in Minitab. There are other measures that are discussed in your textbook, but not included here. One reason is really what using Minitab, and these are the only three ones we can obtain from Minitab. So now formally, let's moving into the models. The first method listed here says moving average. However, I do want to point out there's another method that I even didn't bother to create a slide for. It's called the naive method. Naive. Okay, and I didn't put that method here really because it's naive. As you can imagine, it won't be useful. The naive method basically just means if you want to predict for the next quarter, use current quarter value, and that's it. There's no techniques involved. You just simply say nothing will change in the next quarter, which is quite unlikely to happen. It's very unrealistic. And therefore, usually that's just a very introductory method. So we're gonna skip that and move to the first one that is, at least to a certain extent, useful, moving average. Okay, so the moving average model is usually used for quarterly or monthly data to help smooth the data, okay? Not in particular for forecasting, but it's part of forecasting. Sometimes moving average is involved in other more complicated methods as intermediate step. Okay, it is more about smoothing out the data than really forecasting for future, okay? So when you use moving average method, the prediction for the next period is just the average of the previous K period. And of course, we're gonna determine what the value for K it will be. Okay, you simply add up the previous K values divided by K to get the average, and you say that's the prediction for the next period. One feature, not really a very desirable feature though, is that with moving average, we give equal weight to past values. What does it mean? So let me show you quickly a formula right here. Okay, if you look at the formula for moving average, we're adding the previous K period values divided by K. And you can see for each Y in the numerator, the weight is just 1. Okay, they are weighted equally. And in that sense, we don't care whether it's 1 period ago or 10 period ago. But if you think about the real world situation, most of the time, probably future period value is more related to value 1 period ago than value 10 period ago. So when you give equal weight to past values, you are assuming every period in the previous K period is equally important. All right. Since we're using moving average model for quarterly data or monthly data, we usually pick K to be equal to 4 for quarterly data or 12 for monthly data. So in particular, how do we do the calculation? Well, you've got the formula here. As I said, you add up the first K values, divide by K. Okay, so here I give you an example to show you how manually we calculate the moving average for a particular period, right? So the data is the gasoline purchase for a company, okay? And we have the period denoted by PT. We have number of gallons. And the Y hat here is the prediction using the moving average method, okay? We will pick K equal to 5. So let's do K equal to 5. K equal to 5, and meaning we're taking a 5 period moving average. We're gonna add the previous 5 period together divided by 5. And if we want to predict for period 6, for T equal to 6, we will add up the first 5 values by 5, 4, 3, 2, 1, and they correspond to these values in the table. I'm gonna highlight those, and to 295. You add all of these numbers up and divide by 5 to get 289.8. That is the forecast for the 6th period. And similarly, for the 7th period, we would add up the previous 5 period, meaning we're gonna start from 291 and to all the way to 268. That's 5 of them. That's immediately before the 7th period. We add them up, divide by 5, and we find that forecast to be 288.4. Okay. So that's how we use moving average method to do the forecast. Let's take a look at an example and see how we can use Minitab to do the forecast for us, to run the model for us instead of manually calculate every value. It says the Spokane Transit Authority operates a fleet of vans used to transport both persons with disabilities and the elderly. A record of the gasoline purchased for this fleet of van is collected. The actual amount of gasoline consumed by a van on a given day is determined by the random nature of the cause and the destination. All right, so basically the data, if I pull back, is listed in this table. We're using the same data in this table. We just want to use the moving average method to run the model and to do the forecast. On the left-hand side, you will see this scatter plot showing you how the data look like. My first impression is that the data seems to be stationary. I don't see any upward or downward trend. I don't really see very clearly seasonality, although that is still a question. But it's not our focus, at least for right now. All right, So on the right-hand side, you will see this graph. This is the graph showing the moving average method used. And the number of period we used is 5, okay? And before I move to Minitab, I want to point out that if you look at the if you look at the red curve, that is the moving average, meaning for each dot, that's the average of the previous 5 observations. As you can see, the red curve kind of shows a similar pattern as the original data, but it does not represent the original data that well. It's always coming in late. So the pattern is showing up in later periods than the original data. All right. So let me move to Minitab to do the analysis before we come back and look into the results in more details. Okay, so here's the Minitab with the data file opened. The name of the file is Spokane Transit Authority. There's only one column, including the purchase for 30 observations. What we want to do is a moving average model with 5 periods. So we're gonna go to stat and time series. Then we will pick moving average. It's written here, so click on it. And the variable will be purchase. We do need to define the moving average length, that is 5. There are a couple of options right here. So the first one, center the moving average, basically means if I'm taking the average of 5 periods, I'm gonna report the results in the observation in the middle, right? So you have 1, 2, 3, 4, 5 observations added up. I'm gonna report the results for the third observation, for the third number there. Otherwise, it's usually reported for the very last number used. We're gonna leave it just as default, not center the moving average. The other option you will see is as general focus. This means if we want to use the moving average method to really do the forecast, we will select this and we will specify how many periods we want to focus forward. Right now we have 30 observations. If we want to focus for the next 4 or 5 period, we can put in 5 there, then the results will be forecasted for the next 5 period. Since we are not there yet, so let's just leave it as it is, then click OK. So Minitab will give you some of the specifications we entered and let you know what is carried out. Typically, we can look at the graph to see how the forecast is doing, how the model is doing, and also the measurement for the forecasting errors, right? So we obtained the graph that is the same as the one we just saw on the PowerPoint. So let's return to the PowerPoint and we will go from there. Okay, on the right-hand side, you see the same graph showing us the original data denoted by the blue dots and blue lines, as well as the 5-period moving average denoted by the red dots and the red lines, okay? Several things we can observe. Number one, the forecast, okay, is relatively smoother than the original data, meaning there's less ups and downs, and also the deviation is not very dramatic as the blue ones, right? Some of the blue ones can be as low as 245-ish, but the lowest value for the forecast is around 265, I believe, right? So the original data is more volatile, I would say. After we take the moving average, we'll smooth out some of the bumps after there, okay? The other thing we would observe is that actually the focus is not close to the original observation. Like take this for example, right? Right here is the forecast and the actual value is as high as 300. So there's a big gap between the two. Some of them are kind of smaller. For this observation, the focus is almost the same as the original data, but some of them are really different. So that just tells us moving average, at least for this example, does not do a good job doing the forecast. As I mentioned before, we mainly use moving average as a facilitated or intermediate step for other more complicated or advanced methods. We also use it to smooth out the variations. So we will not use this model to do forecast since it's not that good. But in Minitab, if we do want to use it for forecast, we can just select that choice and specify how many periods we want to do it. All right, so let's move to the next model. It's the exponential smoothing. This model is more widely used than the moving average. The model has several advantages. It is relatively easy to calculate, and we don't require tons of data, so we limited data needed. And a lot of the times, exponential smoothing does give us good results, at least in comparison with moving average. Exponential smoothing is much, much better. But in order to use the exponential smoothing, we're gonna have to assume there's random variation around the stable level. That is, we have to assume the data is stable. We can't incorporate trend or seasonality. Now the good news is, since a lot of the data do involve trend and seasonality, the good news is we can expand the simple exponential smoothing to incorporate trend and seasonality. All right, so in terms of the exponential smoothing, there are 3 of them actually, and the first one is the simple model, which requires stationary data. That is, we assume variation around a constant level, which is really true. Therefore, there are 2 extensions. The first one is the Hauss model. For this one, we can allow for trend. And the last one, the Winters method, allows for both trend and seasonality. So we would first examine our data. If the data shows trend only, we will use Hauss method. And if the data shows both trend and seasonality, we're gonna use the Winters method. If the data is stationary, then the simple model can be used. All right, so I want to start with the simple exponential smoothing, and just to show you what's the difference between this one and the moving average, and also hopefully allows you to kind of realize, oh, that's why this model is doing much better than the moving average. And don't be scared by this formula. It's just for discussion purpose. So what I show here is how the focus is calculated using the simple exponential smoothing. When we were talking about the moving average, I mentioned that for the moving average, we are using the same weight for all past periods. That is, assuming all past periods values are equally important for forecasting for the future. With exponential smoothing, we assume that values closer to the current period is more important than values many periods ago, which kind of makes sense because as things change, the value will change across time. Then apparently, if you want to predict for the future, you want to look into the past couple of periods, but not the past 50 or 60 periods, right? So the more recent values will be more relevant. And that's the basic idea. So in simple exponential smoothing, we will give different weight for different observations, right? Like if we want to predict for the time period t plus one period ahead, we're gonna use the period t value, okay, and we'll assign alpha as the weight. Then for t minus 1, that is 2 periods ago, we assign alpha times 1 minus alpha, another weight. And for 3 periods ago, we will do alpha times 1 minus alpha squared. You would notice that when we pick alpha to be less than 1, which has to be the case, alpha will not be greater than 1. When we pick alpha less than 1, you would notice that these values, the weights, alpha times 1 minus alpha, alpha times 1 minus alpha squared, those weights will decrease gradually. Okay, so our task for simple exponential smoothing will be to determine the alpha. What weight we want to use? Well, you can pick alpha from 0 to 1, theoretically speaking. But what's the difference? How do we determine? Well, I have two tables showing you the difference between a small value of alpha and a large value of alpha. If you pick a small value of alpha, when we pick alpha equals to 0.1, you would notice that for time t, the weight is 0.1. For time t minus 1, the weight is 0.09. And the next one will be 0.08, okay? Now in comparison with alpha equal to 0.9, for the very first period, for the very first one, t, the weight is 0.9. That's much bigger than when alpha is equal to 0.1. And therefore, in a sense, when you pick a large alpha, you are saying the value in the previous one period is the most important one. It's much important than anything else in the model. But when you pick alpha equal to 0.1, we're saying, well, the weight for the value 1 period ahead is important. It is still carries the highest weight, but it's not much larger than the weight given to other values. Okay, so we will take a look at the example later on to see graphically what's the difference between a small alpha and a big alpha. But basically, when we choose alpha close to 1, we put more weights on the more recent values. And if we want to stable the prediction and make it much smoother, we want to pick small value of alpha. In practice, when we manually pick alpha, we just keep our purpose in mind. Do we want a more smooth curve, or do we value recent values more than the rest? And a lot of times, we usually pick alpha from 0.05 to 0.3. And these values typically give us good results. If in any situation we find alpha greater than 0.3 give us the best results, then this usually means maybe we should try another forecasting technique. And that kind of technique may give us even better results. Okay. Let's take a look at an example, and we're going to use the simple exponential smoothing to smooth the curve and see if we can use it for forecast. So quarterly sales of saws from 2000 to 2006 for the Acme tool company are obtained. Let's first examine the data for stationary, trend, and seasonality using time series plot and ACF. So that's the first step. We got the data. We want to examine the data to determine whether there's trend, seasonality, or any other patterns. Okay, since we've done this time series plot and ACF graph a couple of times, so I'm gonna skip showing you the mini tab analysis. We'll just look at the results. By looking at the time series plot, I do observe that there is an upward trend going that way. I also observe certain seasonality because when I look at the pattern, I do see a similar pattern repeat itself. Since it's quarterly data, I observe that every 4 period, the pattern repeats itself. Therefore, I think there's seasonality. When we look at the ACF graph, right? For the trend, it's not very clear because I don't observe what we usually do. That is, we observe significant autocorrelation for the first couple of legs, and then the legs are gradually decreasing. I don't observe that, but I do observe a significant autocorrelation at leg 4. So there's definitely seasonality, okay? Ideally, we would like to use a method that adjusts for seasonality as a minimum, but since we're discussing for the simple exponential method, for practice purpose, let's go ahead and estimate the simple exponential smoothing. What I show here are 2 scenarios for alpha equal to 0.1 and alpha equal to 0.6. We're gonna come back to the results later on to examine the details, but let me move to Minitab and show you how to do this simple exponential smoothing. All right, so this is the other data file that's named Acme Tool Company, and still 1 column showing the sales data. We want to estimate the simple exponential smoothing. So we go to stat and we pick time series. So right below moving average, you will see simple exponential smoothing. That's the one we want to use for right now. Click on it, and the variable is sales. In terms of picking alpha, we can use the default one, which allows Minitab to pick for us. Minitab will determine the optimal alpha level that can be used. There's algorithm behind the scene to do this for us. Or we can pick alpha ourselves. For the sake of discussion, let's pick alpha ourselves and to see what happens. The first one we want to use is 0.1. So let's put 0.1 there and click OK. We do not generate forecast because we're not there yet. Usually we do the forecast after we determine this model is sufficient and does a good job, then we use it for forecast. So click OK. Again, we see some basic information up there and then followed by the graph showing the smoothing. Okay, that's one smoothing model. So the other alpha value we want to use is 0.6. Let's go ahead and do that one. So I'm gonna go to stat time series, simple exponential smoothing, and same variable, but this time I'm gonna pick 0.6 for alpha. And click OK again, we will see a different graph. Big difference, actually. Before we return to PowerPoint, I want to show you quickly, because we will not be switching between Minitab and PowerPoint very frequently. Don't think that's a good idea. I want to show you quickly if we allow Minitab to pick alpha for us. So we're gonna return back to the optimal ARIMA. And by the way, ARIMA is a family of models in forecasting that we will learn toward the end of the semester. So click OK. And turns out the optimal alpha Minitab picked for us is 0.266, okay? It's in between 0.1 and 0.6, and we obtain this graph. All right, so let's return to the Minitab, the PowerPoint, and continue our discussion. So here I put the two results side by side so that we can do the comparison quickly and easily. What you would observe verifies what we just discussed. When you select alpha to be small, that means you are obtaining a more smoothing curve, right? This is very smooth. If you look at the red dots and the red lines, very smooth. But if you pick alpha to be 0.6, meaning you put more weight on recent observations, you will see that the forecast or the estimate still consists of a lot of up and downs. But when you pick alpha to be 0.6, you will see that the forecast or the estimates shows a lot of variations. It can mimic the up and downs in the original data better, of course, at a lagged space, because you will see the same pattern will repeat in later period than the original data. And on the other hand, the curve is not smooth. So next, if you look at the one chosen by Minitab, the value is in between 0.1 and 0.6, and the curve is also in between the previous two. It is smoother than the one with alpha equal to 0.6, and it mimics the up and downs in the original data better than when alpha equal to 0.1. All right, so how do we determine if the model is good or not, right? Do we have any criteria? Well, yes, we do. Actually, one criteria we can look at is the forecasting error reported in the results. We have MAPE, MAD, and MSD. 3 criteria is reported. We can look at the numbers, compare across different models to determine which model is better. So another way to evaluate the model is to examine the residuals. So before we check on the residuals, let me briefly explain what residuals are. Residuals are whatever left in the data after we use the model and remove the systematic patterns. Or in other words, we use the original data, subtract by whatever predicted using our model, whatever left, that's the residual. And you may actually recognize residuals are just the focused errors we talked about earlier. Yes, they are the same. Focused errors are the difference between the actual data and the value forecasted by our model. And the residuals is also the difference between the actual data and the value forecast by our model, because when we use the model to forecast, we actually capture the systematic patterns. And if we remove that part, whatever left is the residuals. When we estimate the model or use a model for the data, our hope is to use the model to capture all systematic patterns in the data. So when we remove such systematic patterns captured by the data, we hope the residue to be random. We hope that we didn't leave any other pattern behind. Because if we have other pattern showing in the residue, that means there's still something we can capture and utilize for forecasting, but wasn't captured by the model. So every time we check the residue, we always want to have the residue to be randomly allocated, showing no systematic pattern. All right, so we can check whether the residuals are random or not using the same 2 graphs that we used for any data set, the time series plot and autocorrelation function for the residual. And I want to move to Minitab as of right now to show you how to obtain the residuals and how to obtain these 2 graphs. Okay, let's just use the last one, the optimal alpha picked by Minitab. Now, in order to obtain the residue, we will need to rerun the model. So let's go to stat, time series, and pick simple exponential smoothing. And before we click OK, we want to hit storage and check on residue. If you've never saved the residue, this box is not checked. So you want to click on it to check it, meaning that we want residue to be saved. So click OK and OK again. And there we go, we got the residues. Okay, so once we have the residues, we can obtain the time series plot and ACA function as the same as we did before. So we go to stat time series and let's get time series plot first. Click OK. And this time we want to use residues instead of sales. So double click on residue to select it and click OK. There we go. Here's the time series plot of the residues. We would also like to get the autocorrelation function for the residues. So now this time the variable is residues. Double click on it and click OK. And there we go. That's the autocorrelation function. All right. So the main step is really to rerun the model, click on storage and select residue to be saved. All right, let's go back to the PowerPoint and continue our discussion. So here we go. I've got the two graphs side by side for us to check the residues. And then on the right-hand side, you see this is the screenshot I put there in case you forget how to get the residues. By looking at the time series plot, I can definitely observe this seasonality still there in the residues is almost the same as the original data, which means even though we use the simple exponential smoothing, we couldn't take care of the seasonality in the data. There's still pattern to be captured, and which is confirmed by the autocorrelation function because we can clearly see this lag at time 4 is significant and bigger than the rest of them. Somehow in the residue, we also observe a negative autocorrelation for lag 2. Regardless, we can confirm that seasonality is still there. And this is not surprising actually, since we know that the simple exponential smoothing is not capable of dealing with seasonality. And therefore we can tell this model is not sufficient. So let's move to the first extension, which take care of the trend, but not the seasonality. Typically, we'll use this model if the data only shows trend, but no seasonality. We can tell right away for the same example, this model will not work well. Again, for the sake of discussion, let's just take a look at this model. For the host, we call it host exponential smoothing, but in Minitab, you will find it labeled as double exponential smoothing. Both means the same thing, which means it takes care of the trend. So for the double exponential smoothing, we have two smoothing factors. One smoothing factor is still alpha, the same one as in the simple exponential smoothing model. The other factor is beta, which is used to capture the trend. And it is just beta that take care of the trend. Okay, for alpha and beta, we either choose them or we can choose them by minimizing MSE, one of the focusing error measurement. Okay, so what we're gonna do is to apply the model to the same data and see what happens. So the host method shows up in Minitab as double exponential smoothing right below the simple exponential smoothing. For a better discussion, allow me to go ahead and talk about the results and move to the very last model, which is the Winters method. Then we're gonna move to Minitab and I will show you how to run these two models together. So let's assume we've already done this. We went to Minitab and obtained the results. And on the left-hand side, this is the model. On the right-hand side, that's the autocorrelation for the residuals. So if you look at the model, alpha is picked to be 0.3 and beta is picked to be 0.1. Although in Minitab, they decided to label this parameter as gamma, but it's virtually beta in our model there. And using this method, what you can see is that the curve is somewhat smoother than the original data, but it's not very smooth, which is okay in the sense that if our purpose is not really smoothing out everything, and there are times where we want the focus to at least capture some of the variations in the original data, okay? And then when we look at the residuals, not surprisingly, we still observe this significant autocorrelation at lag 4, meaning that in the residuals, the seasonality is still there. Since we know the Haas method cannot capture or deal with seasonality, we know this model will not be sufficient. And therefore, we're gonna move directly to the very last method, the Winters method, which apparently adjusts for both trend and seasonality, which should be a good model among the 3 for us to use for the data. Okay, so for this method, there will be 3 components. There's the single exponential factor alpha, there's also the trend beta, and finally there is a third parameter gamma controls for seasonality. And we do need to specify these parameters in Minitab. So let's go ahead and take a look, okay? Same data, this time we want to use the Winters method. Unfortunately for alpha, beta, and gamma, they are labeled as alpha, gamma, and sigma, and delta, sorry. And delta in Minitab, we do have to specify the values ourselves. And unfortunately, there's no golden rule to tell you, well, we should pick this number versus that number. A lot of times we just start from a point and try different numbers, different combination to see which one give us the minimum MSD, mean square deviation. Okay, the combination we picked for our example is 0.4, 0.1, 0.3, and we also obtain the residuals. So let's go ahead and run these models in Minitab. Then we'll come back to examine the results in more details. So the first model we want to estimate is the double exponential smoothing. Let's go to stat, time series, and we're gonna pick double exponential smoothing. So the variable is sales, and you want to double click on sales to have it filled in the box. For double exponential smoothing, we can either allow Minitab to pick the parameters for us, or we can specify the weight. Let's take alpha equal to 0.3 and trend equal to 0.1 and see what happens. So click on OK. There we go. So this is the same as the one I showed you in the PowerPoint slides. The forecast is smoother than the original data, but it's not very smooth. Let's see. What if we allow Minitab to pick the optimal alpha and beta or gamma for us? So go back to double exponential smoothing. This time I want to pick optimal ARIMA and then click on OK. So if we pick the optimal alpha and gamma, it turns out the forecast is even more dramatic than the original data. Since we know double exponential smoothing model does not work for our data, there's no need for us to check the residuals anymore. But just for comparison, if you look at MSD for the second model versus MSD for the first model, you would find out that actually for second model is 28,000, around 29,000. But for the first model is 20,000. So actually, the parameter we put in can better minimize MSD than the parameter picked by Minitab using the optimal algorithm. All right, so lastly, let's do the Winters method. So we'll go back to stat time series and pick Winters method. So the variable is still sales, and we do need to specify the seasonal length. Since we know this is quarterly data, we're gonna put 4 there to denote the seasonality. For Winters method, there's this multiplicative and additive choices. We typically just pick multiplicative. We rarely use additive. So let's just stay with that. And as I said, for alpha, beta, and gamma, for the 3 parameters, we do have to pick our own levels. The one that shows our on the PowerPoint is 0.4, 0.1, 0.3, I believe. And this is just one specification. It doesn't mean you have to just use this one. It could be changed. And this one came up after several tries. Maybe it's the best among the several tries. Since we know the Winters method should be working for our data, so let's go ahead and storage the residuals and store the residuals. Okay, so click on the residuals, click OK, and OK again. So there we go. That's the Winters method. Number 1, I see the curve is just a little bit smoother than the original data. But what's better is that this forecast mimic the original data very well, right? It's very close to the original data. Next, we can check on the residuals. So it's the second residue in the 3rd column. We're gonna do stat time series. We can obtain the time series plot first. So remember to pick residue 2 because that's the new one. Okay. And now this time when I look at this time series plot of the residuals, I don't observe that strong seasonality. There's still some, which means maybe other methods can even better. Or in other words, the Winters method is not sufficient. But then let's check on the autocorrelation for the residuals. Okay. And according to the autocorrelation function, it seems like there's no significant autocorrelation, which tells me, at least in terms of examining the residuals, the model is sufficient for us to use. Okay. And I want to go ahead and show you how to do the forecast since we are already within Minitab. That way we will not need to switch back and forth again. Now, suppose we determine this model is the one to be used. If we want to forecast for the next period, usually we say that's one step ahead, we will need to rerun the model and do the forecast. So we'll go to stat, time series, Winters method. The good thing is we're gonna use just the model we estimated a moment ago. We don't need to specify anything else except for checking on generate forecast. And the number of forecast we want is just 1. We want 1-step forecast. And of course, if you want to forecast for more period, you're gonna put 2, 4, etc. So click on OK. We'll see the same results, but this time we can see the actual forecast. The forecast, it turns to be 778. The good thing is that the result also gives us a interval, a confidence interval. And this is because the forecast is just one number. And if you believe your actual value one step ahead will be 778, then you are seriously wrong. It could be a number close to 778, but most likely it is not. And with the same logic, we want to provide a range saying that for the next period, the predicted value could be between 622 and 933. Okay. Also, when you move to the graph, you would notice that in addition to the forecast for the given data, we also observe one additional observation or forecast there that's for one step further. And these two arrows, kind of purple, pink, my vocabulary in color is very limited, but anyway, these two little marks denote the confidence interval. Okay, so let's go back to PowerPoint, and now we can focus on the discussion exclusively. So back to the Winters method, as we discussed briefly, the forecast mimic the original data very well. It is a little bit smoother than the original data. When we examine the residue, we didn't notice any significant autocorrelation. That means the model is sufficient, and it is the best model so far. We can further confirm that by looking at the forecasting error, the measurement we discussed at the beginning of the chapter. So by looking at the three criteria, what you can see is that the Winters method is definitely the winner, right? If you look at MSD, the Winters method shows a value of 7,223, while the Host method and simple exponential shows values that is as high as 20,000. So definitely the Winters method is the winner. Same for the other two criteria. And therefore, we can use the Winters method to do the forecast, which we already did in Minitab. On this page, it just shows the results. All right, so that's all I have for this chapter. And this is the end. Let me know if you have any questions. Bye.